So here's something worth thinking about as you settle in tonight. Right now, wherever you are, time is passing for you at a very specific rate. And I mean that in a way that's more literal than you might expect. The watch on your nightstand, the clock on your phone, the gentle rhythm of your own heartbeat. They're all ticking along at a pace that belongs to you, in your particular spot in the universe, at this particular moment. And here's the thing. If you were somewhere else, say on top of a mountain, or orbiting the Earth in the International Space Station, or standing on the surface of a neutron star, time would tick differently. Not metaphorically, not in some poetic philosophical sense. Actually, physically, measurably differently. Your heartbeat would still feel normal to you. Your thoughts would flow at what seemed like the usual pace. But compared to someone back here, lying in their bed, time itself would be running at a different speed. That's gravitational time dilation. And it's one of the strangest, most beautiful, most quietly consequential ideas in all of physics. It touches everything from the GPS satellites that guide your car to the way black holes warp space around them, from the ticking of atomic clocks in laboratories to the ultimate fate of stars. And tonight, we're going to walk through it. Slowly, gently, from the very beginning. How people first started thinking about time. How one particular physicist realized that gravity and time are tangled together in ways nobody had imagined, and what that means for the universe you're lying in right now. Let's start way back. And I mean way back. For most of human history, time was simple. It was the sun crossing the sky. It was the seasons turning. It was the steady drip of water through a clepsydra. That's a water clock, the kind the ancient Egyptians and Greeks used, where you'd fill a vessel with water and let it drain through a small hole. And the level of the water told you how much time had passed. Time was something you measured by watching things move. The shadow on a sundial, the swing of a pendulum, the sand falling through an hourglass, and the assumption, the deep, unquestioned assumption underneath all of it, was that time was universal. That a second was a second was a second, everywhere, always, for everyone. That time was like a stage, fixed, unchanging, absolute. And everything in the universe just played out on top of it. Isaac Newton made this explicit. In his Principia, published in 1687, he wrote, and I'm paraphrasing slightly because the original Latin is beautiful but not exactly bedtime reading. He wrote that absolute, true, and mathematical time flows equably without relation to anything external. Flows equably. That's such a wonderful phrase. Time, in Newton's picture, was like a river with a perfectly constant current, carrying everything forward at exactly the same rate. It didn't matter where you were. It didn't matter how fast you were moving. It didn't matter whether you were standing next to a mountain or floating in empty space. Time flowed the same for everyone. And honestly, that's an incredibly intuitive idea. It matches our everyday experience almost perfectly. You and your friend synchronize watches, you go your separate ways, you come back together, and your watches still agree. Of course they do. Why wouldn't they? And for more than 200 years, that was good enough. Newton's mechanics worked spectacularly well. You could use his laws to predict the orbits of planets, the trajectories of cannonballs, the behavior of tides, the clockwork universe, people called it. Everything ticking along in absolute time and absolute space, governed by precise mathematical laws. It was elegant. It was powerful. And it was, in a very specific and important way, wrong. But we'll get to that. Let's stay with Newton for a moment, because his picture of gravity matters for our story too. Newton didn't just describe time. He described the force that would eventually be shown to bend it. His law of universal gravitation, also in the Principia, said that every object with mass attracts every other object with mass. The Earth pulls on you, you pull on the Earth. The Sun pulls on Jupiter, Jupiter pulls on the Sun. And the strength of that pull depends on two things: how much mass the objects have and how far apart they are. Double the mass, double the force, double the distance, and the force drops to a quarter. It's an inverse square law, and it works beautifully. Newton could explain why the moon orbits the Earth, why the planets orbit the sun, why apples fall from trees. All the same force, all the same law. But here's what Newton couldn't explain, and this bothered him, and he was honest about it. He couldn't explain how gravity worked. How does the sun, 93 million miles away, reach out across empty space and pull on the Earth? What's the mechanism? Newton called this action at a distance, and he famously wrote in a letter to Richard Bentley in 1693 that the idea of one body acting on another through a vacuum without any intermediary was so absurd that no person with a competent faculty of thinking could ever fall into it. He knew something was missing. He just didn't know what. And that gap, that mystery of how gravity actually operates, would sit there for more than 2 centuries, waiting for someone to come along and see it completely differently. Now, let's talk about that someone. And let's take our time with him, because his story is genuinely remarkable. Albert Einstein was born on March 14th, 1879, in Ulm, in the Kingdom of Württemberg, in the German Empire. His father, Hermann, ran a small electrochemical business. His mother, Pauline, was a musician. The family moved to Munich when Albert was an infant, and by most accounts he was a quiet, somewhat dreamy child. There's a famous story, probably embellished over the years, but it captures something true, that he didn't speak much until he was 2 or 3, and his parents worried about his development. When he finally did speak, the story goes, he spoke in complete sentences. His first words, supposedly, were a complaint that his milk was too hot. Whether that's exactly true or not, it paints a picture of someone who observed first and spoke only when he had something fully formed to say. That's a quality that would serve him well. When Einstein was about 5 years old, his father showed him a compass. And this is one of those small moments in a life that, looking back, seems to carry enormous weight. The young Einstein was fascinated, deeply, viscerally fascinated, by the fact that the needle always pointed the same direction, no matter how you turned the compass. Something invisible was acting on that needle. Something he couldn't see or touch was reaching through space and exerting a force. He later recalled that this experience made a deep and lasting impression on him. It gave him the sense that behind the things we can see, there are deeper structures, hidden forces, invisible architectures that govern how the world actually works. He was not, by the way, a stellar student in every subject. He clashed with the rigid authoritarian style of German schools. He was brilliant in mathematics and physics, but indifferent to subjects that didn't interest him. And he had a stubborn, questioning temperament that didn't always endear him to his teachers. He eventually left the gymnasium in Munich without finishing. Some accounts say he was asked to leave. Others say he left voluntarily and made his way to Switzerland, where he applied to the Polytechnic in Zurich, one of the finest technical schools in Europe. He failed the entrance exam the first time. He was 16. He passed on his second attempt, enrolled, and graduated in 1900 with a teaching diploma in physics and mathematics. And then, and this is important for understanding how his great ideas came about, he couldn't get an academic job. He applied to universities. He was turned down. He applied for teaching positions. Turned down again. He wrote to professors asking to be taken on as an assistant. Nothing. For a couple of years, he scraped by with temporary teaching gigs and tutoring. It was a difficult, uncertain time. And then, through a connection, a friend's father, he got a job at the Swiss Patent Office in Bern, starting in 1902. He was a technical expert, third class. His job was to evaluate patent applications, to read through proposals for inventions, and assess whether they were sound. Now, you might think this was a dead end for a young physicist. And in some ways, the academic establishment certainly saw it that way. But Einstein later said the patent office was, in its own way, perfect. The work was engaging enough to keep his mind active, but not so demanding that it consumed all his intellectual energy. He could finish his patent evaluations and then spend his remaining mental bandwidth thinking about physics. And he thought about physics constantly, during his lunch breaks, on his walks home, late at night. He had a small circle of friends in Bern. They called themselves the Olympia Academy, which was a grand name for what was basically three guys meeting in an apartment to discuss philosophy, physics, and mathematics over cheap food and strong coffee. And it was during these years, working at the patent office, thinking in his spare time, discussing ideas with his friends, that Einstein produced the most extraordinary burst of creative work in the history of physics. In 1905, his so-called miracle year, he published 4 papers that each would have been enough to make a career. One explained the photoelectric effect using the idea of light quanta that would eventually win him the Nobel Prize. One provided theoretical evidence for the existence of atoms by analyzing Brownian motion. One introduced special relativity, and one gave us E=mc². But tonight, it's that third paper we care about most, special relativity, because that's where the story of time being something other than absolute really begins. Here's what Einstein was grappling with. By the late 1800s, physicists had a problem. James Clerk Maxwell's equations of electromagnetism, published in the 1860s, predicted that light travels at a specific speed, about 186,000 miles per second, or roughly 300,000 kilometers per second. And that speed just appeared in the equations as a constant. It didn't depend on anything. It wasn't relative to anything. It was just the speed of light. Period. But that was strange. Think about it this way. If you're standing on a train platform and a train goes by at 60 miles an hour and someone on the train throws a ball forward at 20 miles an hour, you see the ball moving at 80 miles an hour. Speeds add up. That's just Newtonian mechanics, and it's completely intuitive. So you'd expect the same thing with light. If you're moving toward a beam of light, shouldn't you measure it going faster? And if you're moving away from it, shouldn't it seem slower? But Maxwell's equation said no. The speed of light is the speed of light. It doesn't care how you're moving. Several physicists tried to patch this up. Hendrik Lorentz and George Fitzgerald independently proposed that objects physically contract in the direction of motion, that rulers literally get shorter when they move fast, which would explain why you always measure the same speed of light. Henri Poincaré came tantalizingly close to the full picture. But it was Einstein, in that 1905 paper, who took the bold step. He didn't try to explain away the constancy of the speed of light. He accepted it as a fundamental principle. He said, look, if the speed of light is the same for all observers, no matter how they're moving, then something else has to give. And the thing that gives, the thing that bends and stretches and adjusts to keep the speed of light constant, is time itself. Time, Einstein showed, is not absolute. It's not Newton's river flowing equably for everyone. It's personal. It depends on how you're moving. If you're moving fast relative to me, your clocks tick slower than mine. Not because your clocks are broken, not because of some mechanical effect, but because time itself, for you, is passing at a different rate. This is called time dilation, and in 1905, it was specifically about velocity, about relative motion. The faster you move, the slower your time passes relative to someone at rest. And that was revolutionary. That was earth-shaking. But it was only half the story. Because special relativity dealt with objects moving at constant velocities in the absence of gravity, and Einstein knew, almost immediately, that he needed to go further. He needed to bring gravity into the picture. And the moment he started thinking about gravity, really thinking about it, in that deep, patient, obsessive way of his, he stumbled onto something that would take him 10 more years to fully work out, something that would change our understanding of time even more profoundly than special relativity had. It started with a thought experiment, and it's one of the most famous thought experiments in the history of science. Einstein later called it the happiest thought of his life. He imagined a person falling freely, falling off a roof, say, though he put it more gently than that. And he realized something extraordinary. He realized that a person in free fall doesn't feel their own weight. Think about that for a second. If you're standing on solid ground right now, you feel the floor pushing up against the soles of your feet. You feel the chair pressing against your back. You feel gravity, or at least you think you do. But what you're actually feeling isn't gravity itself. It's the resistance to gravity. It's the ground stopping you from falling. The floor is what you feel, not the earth's pull. Now take the floor away. Imagine you're in an elevator, and the cable snaps, and the whole thing starts plummeting. For those few seconds of free fall, and let's not think too hard about what happens at the bottom. During the fall itself, you would feel weightless. You'd float inside that elevator. A ball you released from your hand would hover right there next to you. Your keys, your phone, a glass of water, everything would just float, because everything is falling together at the same rate, and relative to you, nothing is moving. Einstein grasped something profound in this. He realized that inside that falling elevator, with no windows, no way to see outside, you could not tell the difference between falling in a gravitational field and simply floating in empty space, far from any planet or star, with no gravity at all. The experience is identical. There's no experiment you could perform inside that sealed box that would tell you which situation you're in. And this wasn't just a curiosity. Einstein elevated this to a principle, what he called the equivalence principle. Gravity and acceleration are, in a deep and fundamental sense, the same thing. Let's flip it around, because this works both ways, and the other direction is just as illuminating. Imagine you're in that same sealed box, but now instead of falling, you're out in deep space, far from any star, and someone attaches a rocket to the bottom of the box and accelerates you upward, or what feels like upward, at exactly 9.8 meters per second squared. That's the same acceleration you'd experience from Earth's gravity. Inside the box, you'd feel your feet pressed to the floor. You'd feel weight. You'd drop a ball, and it would fall to the ground. Everything would behave exactly as if you were standing in a room on Earth. And again, no experiment you could do inside that sealed box would tell you whether you're being accelerated by a rocket or held in place by the gravity of a planet beneath you. This is the equivalence principle, and Einstein called the realization of it the happiest thought of his life. He had this insight around 1907, just 2 years after special relativity, while he was still working at the patent office in Bern. And he immediately saw that it had enormous implications. Because if gravity and acceleration are truly equivalent, if they're not just similar but fundamentally indistinguishable, then anything that acceleration does to time, gravity must do too. And here's where it connects back to what he'd already figured out. Special relativity had shown that motion affects time. Acceleration is a form of motion, it's changing motion. So if acceleration affects time and gravity is equivalent to acceleration, then gravity must affect time. Gravity must slow time down. Now, Einstein saw this in 1907. But working it out, actually building the mathematics to describe exactly how gravity warps time and space and the relationship between them, that took him almost another decade. And those years, from roughly 1907 to 1915, were some of the most intellectually grueling years any scientist has ever endured. This wasn't like the miracle year of 1905, where insights seemed to pour out of him. This was a long, grinding, often frustrating slog through some of the most difficult mathematics in existence. Here's the thing about Einstein, and this is a detail people often get wrong about him. He was not, by his own admission, a naturally gifted mathematician. He was a spectacular physical thinker. He could see the physics, the underlying reality, with an intuition that was almost supernatural. But the math was hard for him, and the math he needed for general relativity was extraordinarily hard. He needed to describe curved spacetime, the idea that mass and energy actually bend the fabric of space and time, and the mathematical language for that is something called Riemannian geometry, or more specifically, tensor calculus. This was mathematics that had been developed in the 19th century by Bernhard Riemann and others, originally as pure abstraction, with no particular physical application in mind. And now Einstein needed it, desperately, and he had to learn it almost from scratch. He turned to his old friend Marcel Grossmann, a mathematician he'd known since their student days at the ETH in Zurich, the same Grossmann whose lecture notes Einstein had borrowed because he'd been skipping classes. Grossmann was by this point a professor of mathematics, and when Einstein came to him and said, essentially, "I need a kind of math that can describe curved spaces," Grossmann knew exactly where to point him. He introduced Einstein to the tensor calculus of Ricci and Levi-Civita, to the whole apparatus of differential geometry, and together, between 1912 and 1913, they made significant progress. They published a joint paper, the Entwerf theory, that was a kind of rough draft of general relativity, but it wasn't quite right. Einstein knew it wasn't quite right. There were problems with it. It didn't have the full general covariance he was looking for, meaning the equations didn't look the same in all coordinate systems, which they needed to if the theory was truly going to embody the principle that the laws of physics are the same for all observers. And so began what Einstein later described as some of the most agonizing years of his life. He would try one mathematical approach, follow it for months, convince himself it was wrong, abandon it, try another. He made errors. He published results he later had to retract. At one point in 1913 and 1914, he actually talked himself out of the correct equations. He had them, or something very close to them, and he convinced himself they couldn't be right, and he walked away from them. Imagine that. Holding the answer in your hands and setting it down because you've persuaded yourself it must be flawed. Meanwhile, he was also dealing with enormous personal upheaval. His marriage to Mileva Maric was falling apart. He'd moved from Zurich to Berlin in 1914, partly for a prestigious position at the Prussian Academy of Sciences, but also partly because he'd begun a relationship with his cousin Elsa. Mileva stayed in Zurich with their 2 sons. The First World War broke out. Berlin was tense. Resources were scarce. Many of his colleagues were caught up in nationalist fervor that Einstein, a committed pacifist, found repugnant. And through all of this, he kept working. He kept wrestling with the equations. And then, in the autumn of 1915, things came to a head in the most dramatic way. Einstein learned that David Hilbert, one of the greatest mathematicians alive, was also working on the gravitational field equations, working from the same general principles, but with far superior mathematical tools. There's been a long historical debate about exactly what happened between Einstein and Hilbert in November 1915, who arrived at the final equations first, whether there was any improper exchange of ideas. The consensus among most historians today is that Einstein got there independently, but the pressure of knowing that Hilbert was close, that someone else might publish the correct theory before him after he'd spent 8 years of his life on it, drove Einstein to work at a feverish pace. In November 1915, Einstein gave a series of 4 lectures to the Prussian Academy, each one on a successive Thursday. Each lecture refined and corrected the previous one. He was essentially working out the final form of the theory in real time, in public, week by week. And on November 25th, 1915, he presented the final, correct field equations of general relativity, the Einstein field equations. He later told a friend that he was so excited when he saw that the equations correctly predicted the anomalous precession of Mercury's orbit, a tiny discrepancy in Mercury's path around the Sun that Newtonian gravity couldn't explain, that he had heart palpitations. He said he felt something had snapped inside him. The equations worked. They were beautiful. They were right. So what do these equations actually say? At the deepest level, general relativity tells us that what we experience as gravity is not a force in the traditional sense. It's not like Newton imagined, with masses reaching across space and pulling on each other through some invisible tether. Instead, mass and energy curve space-time itself, and objects move along the straightest possible paths through that curved space-time. The classic analogy, and it's imperfect, but it's useful, is to imagine a heavy bowling ball sitting on a stretched rubber sheet. The ball creates a dip, a curve in the sheet. Now roll a marble nearby. The marble doesn't roll in a straight line anymore. It curves toward the bowling ball, not because the bowling ball is pulling it, but because the surface it's rolling on is curved. The marble is just following the shape of the sheet. Space-time works something like that, though in 4 dimensions instead of 2, which is where the analogy starts to strain. The Sun curves the space-time around it, and the Earth follows a curved path, an orbit, not because the Sun is pulling on it with some mysterious force, but because the Earth is moving along the most natural path through curved space-time. In a sense, the Earth is going straight. It's space-time itself that's bent. And here's the crucial part for our story, the part about time. When space-time curves, it's not just space that bends. Time bends too. In fact, in many situations, the time part of the curvature is more significant than the space part. Near a massive object, near a planet, a star, a black hole, time runs slower. Not metaphorically. not as an illusion. Actually, physically slower. A clock near a massive object ticks fewer times than an identical clock far away from that mass. And this isn't because the clock is broken or affected by heat or pressure or anything mechanical. It's because time itself, the actual passage of moments, is slower in stronger gravitational fields. This is gravitational time dilation. And unlike the velocity-based time dilation from special relativity, this one doesn't require anything to be moving at all. You can be standing perfectly still on the surface of the Earth, and your time is passing more slowly than the time of someone floating in deep space, far from any significant mass. The deeper you are in a gravitational field, the closer you are to the massive object creating the curvature, the slower your time flows. Now, Einstein predicted this in 1915. He could calculate exactly how much time should slow down at a given distance from a given mass. But predicting something and proving it are two very different things, especially when the effect is incredibly tiny. On the surface of the Earth, gravitational time dilation is real, but it's minuscule. We're talking about differences of nanoseconds over extended periods. In 1915, there was no clock precise enough to measure such small differences. So for decades, gravitational time dilation remained a prediction. A beautiful, mathematically elegant prediction that most physicists believed was correct, but that no one had directly confirmed. The first real test came not from clocks, but from light, and it involved something Einstein himself had predicted back in 1911, years before he even finished the full theory of general relativity. He realized that if time runs slower in a gravitational field, then light climbing out of a gravitational field should lose energy. And when light loses energy, its frequency drops. It shifts toward the red end of the spectrum. This became known as gravitational redshift, and it's one of the most direct, elegant consequences of gravitational time dilation. Let me walk you through why it happens, because it's actually a beautifully simple idea once you see it. Think of light as a wave, right? It has a frequency, the number of wave crests that pass a given point each second. Now imagine a light source sitting on the surface of a very massive star, emitting light at a particular frequency. That light is being produced in a region where time runs slowly because the gravitational field is strong. The light then travels upward, away from the star, climbing out of the gravitational well. Eventually, it reaches an observer far away, floating in a region where gravity is much weaker and time runs faster. Here's the thing. From the perspective of the distant observer, the light was produced in a region where time was sluggish. The oscillations of the light wave were happening in slow time, so when those oscillations arrive in the faster time region, they appear stretched out. The frequency is lower. Lower frequency means redder light. The light has been redshifted, not because it lost energy in some mechanical way, but because it was born in a region where time itself was moving slowly. And this is what's so beautiful about it. Gravitational redshift isn't really a separate phenomenon from gravitational time dilation. It is gravitational time dilation, just observed through the behavior of light. You're literally watching time differences manifest as color changes in starlight. That's remarkable when you sit with it. Now, Einstein predicted this effect, and he knew that one place to look for it was in the light coming from very dense stars. The denser and more massive the star, the stronger the gravitational field at its surface, and the more the light should be redshifted when it reaches us. The most obvious candidate was white dwarf stars. These are stars that have exhausted their nuclear fuel and collapsed down to roughly the size of the Earth, but they retain a significant fraction of the sun's mass. That means their surface gravity is enormous compared to a normal star, and the gravitational redshift of their light should be measurable. The star that astronomers focused on was Sirius B, the faint companion of Sirius, the brightest star in the night sky. Sirius B is a white dwarf, and by the 1920s, astronomers had a reasonable estimate of its mass and radius. In 1925, the astronomer Walter Adams at Mount Wilson Observatory in California attempted to measure the gravitational redshift of light from Sirius B. He reported a result that seemed to agree with Einstein's prediction, and for decades, this was cited as one of the key confirmations of general relativity. But here's where the story gets a little more complicated, and honestly, a little more human. Later analyses suggested that Adams's original measurement was probably contaminated by light from Sirius A, the much brighter primary star, which was so close in the sky that its light bled into the observations of the faint companion. The agreement with Einstein's prediction may have been partly coincidental, or partly influenced by the fact that Adams knew what result he was looking for. This is a real issue in science, confirmation bias. And it's not that Adams was being dishonest. It's that when you're working at the very edge of what your instruments can do, and you have a theoretical prediction in mind, it's remarkably easy to unconsciously nudge your analysis toward the expected answer. Better measurements of Sirius B's gravitational redshift came much later, in the 1960s and 1970s, and they did confirm the prediction, but with more reliable data and better techniques. So the early observational evidence for gravitational redshift was suggestive, but not airtight. The really convincing laboratory test didn't come until 1959, and it happened in a tower at Harvard University. This is one of those experiments that's so clever, so elegantly simple in concept, that it deserves some time. Robert Pound and Glenn Rebka. Pound was a physicist at Harvard, and Rebka was his graduate student. They set up an experiment in the Jefferson Tower, a building on the Harvard campus. The tower was about 22.5 meters tall, which is not very tall at all, maybe 7 or 8 stories. And what they did was send gamma rays from the top of the tower to the bottom and from the bottom to the top, and measure whether the frequency of the gamma rays changed during the journey. Now, 22.5 meters of height difference on the surface of the Earth. That's a tiny, tiny difference in gravitational potential. The difference in the rate of time between the top and bottom of that tower is absurdly small. We're talking about a fractional change of about 2.5 parts in 10 to the 15th power. That's 0.00000000000000025. Essentially nothing, right? How could anyone possibly measure that? This is where a piece of physics discovered just a year earlier made the whole thing possible. In 1958, Rudolf Moosbauer, a German physicist working on his doctoral thesis, discovered something remarkable about how certain atomic nuclei emit and absorb gamma rays. Normally, when a nucleus emits a gamma ray, it recoils, like a gun kicking back when it fires a bullet. That recoil steals a little energy from the gamma ray, shifting its frequency slightly. And when another nucleus tries to absorb that gamma ray, it also recoils upon absorption, requiring a slightly different frequency than what was emitted. These recoil effects blur the frequency enough that you can't use nuclear gamma ray emission as a precise frequency standard. But Moosbauer found that if the emitting nucleus is locked into a crystal lattice, embedded in a solid, then the recoil is absorbed by the entire crystal, not just the individual atom. And since the crystal is enormously more massive than a single atom, the recoil becomes negligible. The the gamma ray comes out with an incredibly precise, sharp frequency. And the same thing works in reverse for absorption. This is called the Mössbauer effect, and it essentially gave physicists an incredibly precise frequency source and detector for gamma rays. It was like going from a blurry flashlight to a laser. Mössbauer won the Nobel Prize for this in 1961 at the age of 32, and it was richly deserved. Pound and Rebka used iron-57 nuclei, which emit gamma rays at a very specific frequency. They placed the source at the top of the tower and the detector at the bottom. According to Einstein's prediction, the gamma rays falling downward, moving deeper into Earth's gravitational field, should gain energy, which means their frequency should increase slightly. They should be blue shifted, and the detector at the bottom, sitting in slightly slower time, should see the incoming gamma rays at a slightly higher frequency than what was emitted. The beauty of the Mössbauer effect is that the emission and absorption lines are so incredibly sharp that even this minuscule frequency shift, those 2.5 parts in 10 to the 15th, was enough to knock the gamma rays out of perfect resonance with the absorber. Pound and Rebka could measure whether the gamma rays were being absorbed by the detector, and by carefully adjusting the velocity of the source, physically moving it up and down very slightly to add a Doppler shift that would compensate for the gravitational shift, they could determine exactly how much the frequency had changed. And it worked. Their result agreed with Einstein's prediction to within about 10%. A few years later, Pound and his colleague, Joseph Snyder, refined the experiment and got agreement to within about 1%. This was the first precise, controlled, laboratory confirmation of gravitational redshift, and by extension, of gravitational time dilation. It happened in a tower shorter than most apartment buildings, using gamma rays and crystals and extraordinary cleverness. And think about what they were actually measuring: the difference in the flow of time between the top and bottom of a 22.5-meter tower. Time at the bottom of that tower runs slower than time at the top by an amount so small that it took the sharpest frequency tool in all of physics to detect it. But it's there. It's real. Now, the Pound-Rebka experiment confirmed gravitational redshift, which is a consequence of gravitational time dilation. But what physicists really wanted was to directly compare clocks at different heights, to put an actual clock down low and an actual clock up high and watch one fall behind the other. That required clocks far more precise than anything available in 1959. It would take another decade and a half, and it would involve putting clocks on airplanes and flying them around the world. This brings us to one of the most famous experiments in the history of physics, the Haffel-Keating experiment of 1971. And the story behind it is wonderfully scrappy and improbable. Nothing like the image of big-budget government science you might expect. Joseph Haffel was a physicist at Washington University in St. Louis, and Richard Keating was a scientist at the United States Naval Observatory in Washington, D.C. Haffel had been thinking about whether commercially available cesium atomic clocks, which by the early 1970s were portable, about the size of a large suitcase, were precise enough to detect relativistic time dilation effects during ordinary airline flights. Not rocket ships, not particle accelerators, commercial airline flights. The kind you and I would take. The idea was deceptively simple. Take 4 cesium beam atomic clocks. Leave a reference set of clocks at the Naval Observatory. Fly the portable clocks around the world on regular scheduled airline flights, once going eastward, once going westward. Then bring them back and compare them to the reference clocks. According to relativity, there should be measurable differences, and the eastward and westward trips should show different effects, because the velocity-based time dilation from special relativity and the gravitational time dilation from general relativity would combine differently depending on the direction of travel relative to Earth's rotation. Here's what makes this story so endearing. Hoffley and Keating didn't have some massive research grant. They bought regular commercial airline tickets for themselves and their clocks. The clocks each got their own seat. Hoffel later described how flight attendants would ask about the strange equipment, and he'd explain that he was testing Einstein's theory of relativity. Some of them thought he was joking. The total cost of the airline tickets was something like $8,000, which even in 1971 was modest for a physics experiment of this significance. Now, the predictions were specific. For the eastward trip, the clocks were moving faster relative to the non-rotating frame. They were adding their flight speed to the Earth's rotational speed. This meant more velocity-based time dilation, which slows time down. But they were also at altitude, about 30,000 feet, where gravity is slightly weaker, which means time runs slightly faster due to less gravitational time dilation. For the westward trip, the clocks were moving slower relative to the non-rotating frame, subtracting their flight speed from Earth's rotation, so the velocity effect was smaller, and the gravitational altitude effect dominated. The prediction was that the eastward flying clocks would come back behind the reference clocks, having aged less, and the westward flying clocks would come back ahead, having aged more. And when they brought the clocks home and compared them, the results matched the predictions. The eastward clocks had lost about 59 nanoseconds. The westward clocks had gained about 273 nanoseconds, both within the range of experimental uncertainty of what relativity predicted. Nanoseconds, billionths of a second, accumulated over days of flying around the entire planet. But they were real, and they were measurable, and they matched the theory. This was 1971, and for the first time, human beings had directly watched clocks run at different rates because of differences in both speed and gravitational potential. Both flavors of time dilation, special and general, confirmed in a single experiment using equipment you could carry onto a Pan Am flight. There's something deeply satisfying about that. The most profound insight about the nature of time, tested with suitcase-sized clocks and coach-class airline tickets. But the Hoffel-Keating experiment, as celebrated as it was, had significant uncertainties. The clocks weren't perfect, the flight paths were complicated, and the analysis required careful accounting for many variables. Some critics questioned whether the uncertainties were too large to be truly convincing. The physics community generally accepted the results, but everyone knew that better tests were needed. And those better tests would come from an unexpected direction, not from pure physics research, but from a practical engineering problem that the United States military was trying to solve. A problem that would eventually put relativistic time dilation into the daily life of essentially every person on Earth. And it started with satellites and a system that would eventually be called the Global Positioning System, GPS. And the story of how GPS came to depend on Einstein's general relativity is one of the most beautiful examples in all of engineering of how pure theoretical physics, the kind that seems abstract and disconnected from everyday life, can suddenly become the thing standing between a system that works and a system that's completely useless. So let's talk about how GPS actually works, because once you understand the mechanism, you'll see exactly where time dilation sneaks in and why it matters so much. The basic idea behind GPS is elegant. You have a constellation of satellites, currently around 31 active ones, orbiting Earth at an altitude of roughly 20,200 kilometers, which is about 12,550 miles up. That's way above the International Space Station, way above weather satellites. These are in what's called medium Earth orbit, and each one circles the planet about twice a day. Every satellite carries an extremely precise atomic clock, and every satellite is constantly broadcasting a signal that essentially says two things. Here's who I am, and here's exactly what time it is right now according to my clock. Your GPS receiver, the one in your phone, in your car, in that little handheld unit hikers carry, picks up these signals from multiple satellites simultaneously. And here's the clever part. Because the signals travel at the speed of light, and because your receiver knows exactly when each signal was sent, that's the timestamp in the message. It can calculate how long each signal took to reach you. Multiply that travel time by the speed of light, and you get the distance between you and that satellite. Do this with 4 or more satellites, and you can triangulate your position in 3 dimensions: latitude, longitude, and altitude. The math is essentially solving a system of equations. If I'm this far from satellite A, this far from satellite B, this far from satellite C, and this far from satellite D, then there's only one point in space where all those distances intersect. That's where I am. Now think about what that means for the clocks. The whole system is built on measuring the travel time of radio signals moving at the speed of light. Light covers about 30 centimeters, roughly 1 foot, in a single nanosecond. 1/1000th of a second corresponds to 1 foot of distance. So if you want your position accurate to, say, a few meters, you need your timing accurate to within about 10 nanoseconds. That's the budget. 10 billionths of a second. Any timing error larger than that, and your calculated position starts drifting. An error of 100 nanoseconds puts you off by 30 meters. An error of a microsecond, a millionth of a second, puts you off by 300 meters. That's 3 football fields, and if the timing errors accumulate uncorrected, the whole system becomes worthless within hours. And this is exactly where Einstein walks into the room. Remember, those GPS satellites are up at 20,200 kilometers. They're significantly farther from Earth's center than you are standing on the surface. They're higher up in the gravitational well. And what does general relativity tell us? Clocks higher in a gravitational field, farther from the massive object, tick faster than clocks lower down. The satellite clocks, sitting way up there in weaker gravity, are ticking faster than your clock down here on the ground. How much faster? About 45 microseconds per day, 45 millionths of a second, every single day. That might not sound like much in human terms, but in GPS terms, where a nanosecond equals a foot, 45 microseconds is 45,000 nanoseconds. That's roughly 13.5 kilometers of position error per day, just from gravitational time dilation alone. 13.5 kilometers every day, accumulating. But wait, there's also the special relativistic effect, the one from velocity. Those satellites are moving at about 3.9 kilometers per second relative to the ground. That's fast. And special relativity says moving clocks tick slower. This effect works in the opposite direction from the gravitational one. It makes the satellite clocks tick slower relative to ground clocks, not faster. The magnitude of this velocity-based slowing is about 7 microseconds per day. So you've got 2 competing effects. Gravity speeds the satellite clocks up by about 45 microseconds per day. Velocity slows them down by about 7 microseconds per day. The net result is that the satellite clocks tick faster than ground clocks by roughly 38 microseconds per day. 38 millionths of a second. And if you don't correct for this, your GPS position drifts by something like 10 kilometers per day. By the end of a week, your phone would think you're in a different city. Here's what's really beautiful about this. The engineers who designed GPS knew about these relativistic effects before the first satellite ever launched. This wasn't a surprise they discovered after the fact. The system was designed from the beginning to account for general and special relativity. And the primary way they handle it is wonderfully simple. They just tune the satellite clocks to tick at a slightly different frequency before launch. The cesium and rubidium atomic clocks on the satellites are deliberately set to run slightly slow compared to their nominal frequency, so that once they're up in orbit, the combined relativistic effects bring them into sync with ground-based time. The ground frequency for the GPS signal is 10.23 megahertz. The satellite clocks are set to 10.22999999543 megahertz before launch. That tiny offset, less than 5/1000ths of a hertz, is the correction for relativity. And it works. Once the satellite reaches its orbital altitude and velocity, that pre-adjusted frequency, warped by gravitational time dilation, speeding it up, and velocity time dilation slowing it down, lands right on 10.23 megahertz as measured from the ground. Think about that for a second. Every GPS satellite ever launched has had its atomic clock deliberately detuned to compensate for the curvature of spacetime. Einstein's 1915 theory, born from thought experiments about elevators and falling painters, is literally baked into the hardware of the navigation system that tells your rideshare driver where to pick you up. If you turned off the relativistic corrections, GPS would degrade so quickly it would be operationally useless within a day. Now, the story of how this actually played out during the development of GPS is fascinating because not everyone was convinced the relativistic corrections were necessary. The program that became GPS started in the early 1970s. The Department of Defense began working on what was initially called the Navstar Global Positioning System. The concept built on earlier satellite navigation systems, particularly the Navy's transit system, which had been operational since the 1960s. Transit used Doppler shift measurements from satellites in low Earth orbit, and it worked, but it was slow. You might have to wait 15 minutes or more for a position fix, and the accuracy was limited. GPS was designed to be faster, more accurate, and available continuously anywhere on Earth. The first experimental GPS satellite, known as NTS-2, Navigation Technology Satellite 2, was launched in June 1977. And here's where the story gets interesting. The satellite carried cesium atomic clocks, and the engineers had included the ability to turn the relativistic frequency offset on or off. There was genuine debate within the program about whether the relativistic corrections were really needed. Some engineers were skeptical, not because they doubted Einstein's physics necessarily, but because the effects were so small, and there were so many other sources of error in the system: atmospheric delays, multipath reflections, orbital uncertainties, that some people thought the relativistic corrections might be lost in the noise. Why add complexity for an effect you might never see? So they launched NTS-2 with the relativistic correction turned off. They let the clock run at its nominal ground frequency and watched what happened. And what happened was exactly what relativity predicted. The satellite clock drifted away from ground-based time at a rate consistent with the 38 microsecond per day prediction. After about 20 days, the accumulated error was large enough to be unmistakable. The relativistic effect wasn't lost in the noise at all. It was the dominant source of timing error. They turned on the frequency offset, and the clock fell into step with ground time. It was a beautiful, almost poetic confirmation. The engineers had essentially run the Hafel-Keating experiment again, but with better clocks, a more controlled environment, and a practical system that depended on getting the answer right. This story gets told sometimes as if the engineers were foolish for doubting relativity, but that's not really fair. Good engineering is empirical. You test things, you verify. The fact that they built in the ability to toggle the correction on and off shows they were being careful, not careless. They wanted to see the effect with their own data in their own system before committing to it. And when the data came in, they committed. There's a physicist named Neil Ashby at the University of Colorado who spent decades working on the relativistic aspects of GPS. He's written extensively about all the subtle effects that have to be accounted for, and it goes deeper than just the basic rate offset. There's the Sagnac effect, which arises because the Earth is rotating and the signals are traveling in a rotating reference frame. There's the fact that satellite orbits aren't perfectly circular. They're slightly elliptical, which means the satellite's altitude and velocity are constantly changing slightly, and so the relativistic corrections vary over the course of each orbit. The onboard clocks handle the average correction through that pre-launch frequency offset, but the residual oscillation due to orbital eccentricity has to be calculated and corrected by the receiver in real time. And there are even smaller effects, second-order Doppler shifts, tidal effects from the moon and sun slightly warping spacetime near Earth, the gravitational influence of Earth's oblateness. Most of these are tiny, but in a system where nanoseconds matter, tiny effects can accumulate. And this is what makes GPS such a remarkable engineering achievement. It's not just a navigation system. It's a relativistic physics experiment running continuously, all day, every day, involving dozens of satellites and billions of receivers, all of them implicitly relying on the fact that spacetime is curved and time runs at different rates depending on where you are in a gravitational field. Every time you open a Maps app, every time a plane lands using GPS-guided approach, every time a farmer uses precision GPS to plant crops in rows accurate to 2 centimeters, all of that works because the engineers took Einstein seriously and built his corrections into the system from the ground up. And GPS isn't the only place where gravitational time dilation shows up in practical engineering. There's another domain where the precision of timekeeping has become so extraordinary that relativistic effects aren't just detectable, they're unavoidable. And that domain is the world of modern atomic clocks, which have gotten so astonishingly precise in the last couple of decades that they can now detect the difference in the flow of time between 2 points separated by just a few centimeters of height. Just centimeters. Let that sink in for a moment. We went from Pound and Rebka measuring time dilation across a 22.5-meter tower in 1959 and calling it one of the most precise measurements ever made, to modern clocks that can feel the difference in time's flow across the height of a small step stool. The story of how we got there is one of the most quietly astonishing chapters in the history of precision measurement, and it's worth slowing down for. So let's talk about what an atomic clock actually does, because the basic idea is beautifully simple, even though the execution is extraordinarily difficult. Every atom of a given element has electrons that can jump between specific energy levels. When an electron drops from a higher energy level to a lower one, or absorbs energy and jumps up, it emits or absorbs a photon at a very specific frequency. That frequency is determined by quantum mechanics. It's a property of the atom itself, not something that changes based on how you built the clock or what factory it came from. A cesium-133 atom in Tokyo behaves exactly the same as a cesium-133 atom in Boulder, Colorado. The transition frequency is a universal constant, and that's what makes it such a perfect basis for timekeeping. You're not relying on a pendulum that might expand in the heat, or a quartz crystal that ages slightly over the years. You're relying on a fundamental property of nature. The standard cesium clock, the kind that has defined the second since 1967, works by tuning a microwave signal until it matches the resonant frequency of cesium-133 atoms. Specifically, the transition between two hyperfine ground states, which vibrates at exactly 9,192,631,770 cycles per second. That number is the literal definition of 1 second. When your microwave signal is perfectly tuned to that frequency, the maximum number of cesium atoms make the transition, and the clock locks onto that signal. It counts 9,192,631,770 oscillations and says, that was 1 second. And cesium clocks got remarkably good. By the 1990s, the best cesium fountain clocks, where you toss a ball of laser-cooled cesium atoms upward in a fountain-like arc so they spend more time in the microwave field, were accurate to about 1 part in 10 to the 15th. That means they'd gain or lose about 1 second every 30 million years, which is extraordinary, but it turns out you can do much, much better. Here's where the story takes a turn that I find genuinely thrilling. Starting in the late 1990s and accelerating through the 2000s and 2010s, physicists began building a fundamentally different kind of atomic clock, one that operates not with microwaves, but with visible light. These are called optical clocks, or optical lattice clocks. And the basic insight is almost embarrassingly straightforward once you hear it. The frequency of visible light is about 100,000 times higher than the frequency of microwaves. If you're counting oscillations to measure time, and your oscillations are 100,000 times faster, then you can slice time into pieces that are 100,000 times thinner. It's like measuring a length with a ruler that has 100,000 times more tick marks per inch. Your resolution just explodes. But here's the thing. Counting oscillations of visible light is absurdly hard. Light in the optical range oscillates at hundreds of trillions of cycles per second. For decades, nobody had a practical way to count those oscillations accurately. You can't just hook up an electronic counter to something vibrating at 500 trillion hertz. The electronics can't keep up. So optical transitions were known to be incredibly precise, but there was no way to read them out, no way to connect that optical frequency to something you could actually use as a clock signal. The breakthrough that changed everything came from an unexpected direction, and it earned its inventors the Nobel Prize in Physics in 2005. It's called the optical frequency comb, and it was developed primarily by John Hall at GILA in Boulder, Colorado, and Theodor Hensch in Munich. The idea is gorgeous. You take a special kind of laser called a mode-locked femtosecond laser, a laser that emits extremely short pulses of light, each lasting just a few quadrillionths of a second. Because of the way these pulses are spaced in time, the laser's spectrum in frequency space isn't a single color, but a whole series of evenly spaced sharp lines, like the teeth of a comb. Hence the name, frequency comb. And if you know the spacing between the teeth and the position of one tooth, you know the exact frequency of every single tooth in the comb. It's like a ruler for light frequencies. You can take your optical clock's incredibly high frequency and use the comb to connect it, rung by rung, all the way down to a microwave frequency that electronics can count. The frequency comb is the bridge between the optical world and the electronic world, and without it, optical clocks would still be laboratory curiosities. So once you have the frequency comb, You can build a clock around an optical transition. And that's exactly what groups around the world started doing. One of the most successful approaches uses strontium atoms, specifically strontium-87. You cool a cloud of strontium atoms down to temperatures just barely above absolute zero using lasers. Then you trap them in an optical lattice, which is essentially a grid made of intersecting laser beams that holds the atoms in place like eggs in a carton. The lattice laser is tuned to a very specific, magic wavelength where it holds the atoms without disturbing the clock transition. This is crucial because you don't want the trapping laser to shift the very frequency you're trying to measure. Then you probe the atoms with an incredibly stable clock laser tuned to the strontium optical transition at about 429 terahertz. When the laser frequency exactly matches the atomic transition, the atoms absorb the light and jump to the excited state. You detect that, and you lock the laser to that frequency. The frequency comb reads out the laser frequency, and you have a clock. And how good are these clocks? This is where things get almost surreal. By 2018, the strontium optical lattice clock, built by Jun Ye's group at JELA, the same lab in Boulder where Hall did his frequency comb work, achieved a precision of about 1 part in 10 to the 18th. Let me put that in perspective. 1 part in 10 to the 18th means the clock would neither gain nor lose a second in roughly 15 billion years. That's longer than the current age of the universe. The universe is about 13.8 billion years old. This clock is accurate to a level that exceeds the age of everything that exists. And there are other optical clocks using different atoms, ytterbium, aluminum ions, that have reached similar or even better performance. Now, here's where this connects back to gravitational time dilation in a way that's just beautiful. When your clock is this precise, general relativity isn't some exotic correction you have to worry about for satellites 20,000 kilometers up. It's right there in your lab. A clock that's accurate to 1 part in 10 to the 18th can detect the gravitational time dilation caused by raising it just 1 centimeter higher in Earth's gravitational field. 1 centimeter. The difference in the rate of time between your desk and a point 1 centimeter above your desk is real, and these clocks can see it. In 2010, a team at NIST, the National Institute of Standards and Technology, also in Boulder, led by Till Rosenband and James Chinwen Chow, demonstrated exactly this. They compared 2 optical clocks, one based on an aluminum ion and one based on a magnesium ion, and showed that raising one clock by just 33 centimeters, about a foot, produced a measurable difference in the rate of time. The higher clock ticked faster, exactly as Einstein predicted. The fractional frequency difference was about 4 parts in 10 to the 17th. They published the result in Science, and it was a landmark moment. For the first time, gravitational time dilation had been measured not between a tower's basement and its roof, not between the ground and a flying airplane, not between Earth's surface and an orbiting satellite, but across a height difference you could span with your forearm. Think about what that means for a second. Time is literally flowing at a different rate at the height of your head compared to the height of your feet. The difference is incomprehensibly tiny. Your head ages faster than your feet by something like 90 billionths of a second over a typical human lifespan. You will never feel it. But it's real. It's measurable. And these clocks prove it. And this isn't just a party trick for physicists. This level of precision opens up practical possibilities that sound like science fiction. One of the most exciting is called relativistic geodesy, or sometimes chronometric leveling. The idea is that if you can measure time dilation with enough precision, you can use clocks as gravity sensors. You place ultra-precise optical clocks at different locations. Compare their tick rates. And from the frequency difference, you can determine the difference in gravitational potential between those locations. That tells you about the shape of Earth's gravitational field, which tells you about the distribution of mass underground, mountains, ocean trenches, magma chambers, mineral deposits, changes in groundwater levels. Traditional geodesy uses satellites and gravimeters to map Earth's gravitational field, but optical clocks could eventually provide a complementary method with extraordinary sensitivity. There's a group at the Physikalisch-Technische Bundesanstalt in Germany, the PTB, which is basically Germany's equivalent of NIST, that has been working on exactly this. They've been comparing optical clocks over long distances using fiber optic links, measuring the gravitational potential difference between labs hundreds of kilometers apart, and their results agree with traditional geodetic surveys to within a few centimeters of equivalent height. It's still early days, but the trajectory is clear. Clocks are becoming gravity sensors. And here's something else that these ultra-precise clocks are starting to make possible, something that connects back to the very foundations of physics in a way that would have fascinated Einstein. When you have clocks this good, you can start testing whether the fundamental constants of nature are actually constant. Are they the same everywhere? Have they changed over the history of the universe? The fine structure constant, the electron to proton mass ratio. These numbers determine how atoms behave, and if they were even slightly different, the universe would look completely different. Some theories of physics beyond the standard model predict that these constants might drift very slowly over time, or might vary slightly depending on your position in a gravitational field. Optical clocks are now precise enough to look for those drifts. Groups at NIST, PTB, the National Physical Laboratory in the UK, and laboratories in Japan and France are all running long-term comparisons between different types of optical clocks, watching for any hint that the constants are shifting. So far, no definitive drift has been found, which itself is a powerful constraint on new physics. But the search continues, and the clocks keep getting better. And there's yet another frontier where gravitational time dilation and precision timekeeping are converging, one that takes us away from Earth entirely and out into the deeper fabric of the cosmos. Because the same relativistic effects that GPS engineers had to account for, the same time dilation that Pound and Rebka measured in their tower, the same curvature of space-time that Einstein spent 8 years wrestling into mathematical form. All of that plays a role in one of the most dramatic astronomical phenomena ever observed. And that phenomenon involves objects where gravity is not the gentle, barely noticeable force we experience here on Earth's surface, but an almost incomprehensibly intense warping of space-time itself. I'm talking about neutron stars, and if you want to see gravitational time dilation taken to its absolute extreme, short of a black hole, neutron stars are where you look. So let's talk about what a neutron star actually is, because the engineering of nature here is almost absurd. When a massive star, something maybe 8 or 10 times the mass of our sun, reaches the end of its life, it runs out of fuel. The nuclear fusion that's been holding it up against its own gravity for millions of years just stops. And when that outward pressure disappears, the core collapses. We're talking about a ball of matter, roughly the mass of the sun, compressing itself down into a sphere maybe 20 kilometers across. 20 kilometers. That's about the distance you might drive to get to work. And into that tiny volume, you've packed more mass than our entire sun. The density is staggering. A teaspoon of neutron star material would weigh something like 1 billion tons on Earth. The atoms themselves can't even exist as atoms anymore. The electrons get crushed into the protons, forming neutrons, and the whole thing becomes this incredibly dense ball of neutron-rich matter, held up against further collapse only by quantum mechanical pressure, something called neutron degeneracy pressure. Now, here's where our story connects. The surface gravity of a neutron star is roughly 200 billion times the surface gravity of Earth. 200 billion. And you already know what strong gravity does to time. If you could somehow stand on the surface of a neutron star, which you couldn't, because you'd be flattened into a film of atoms thinner than a sheet of paper. But if you could, your clock would run noticeably slower compared to a clock far away in flat spacetime, not by microseconds per day, like the GPS satellites, not by the tiny fractions that Chu and Rosenband measured over 33 centimeters. On a neutron star, time runs roughly 10 to 30% slower than it does far from the star, depending on the mass and radius. That's a huge effect. A clock on the surface ticking out what feels like 1 second would correspond to maybe 1.2 or 1.3 seconds for a distant observer. You'd literally watch someone on a neutron star aging more slowly than you, in a way you could perceive without any fancy instruments. And we've actually observed consequences of this. Neutron stars that spin rapidly, pulsars, send out beams of radiation like cosmic lighthouses, and the timing of those pulses is extraordinarily precise. Some millisecond pulsars are so regular that they rival atomic clocks in their stability. When astronomers study binary pulsar systems where two neutron stars orbit each other, they have to account for gravitational time dilation to make sense of the pulse arrival times. The pulses from the neutron star deeper in the gravitational well arrive slightly redshifted, slightly stretched, compared to what you'd expect if spacetime were flat. This is the same gravitational redshift that Pound and Rebka measured in their tower at Harvard. The same physics, just cranked up to an extraordinary degree. One of the most celebrated binary pulsar systems is the Hulse-Taylor pulsar, discovered in 1974 by Russell Hulse and Joseph Taylor, using the Arecibo radio telescope in Puerto Rico. Hulse was actually a graduate student at the time. Imagine being a grad student and stumbling onto one of the most important astronomical discoveries of the 20th century. What they found was a pulsar in orbit with another neutron star, and by carefully tracking the pulse timing over years, they could measure the orbital parameters with incredible precision. And here's what made it historic. The orbit was shrinking. The two neutron stars were spiraling toward each other, losing energy at exactly the rate that general relativity predicted they should lose energy by emitting gravitational waves. This was the first indirect evidence for gravitational waves, and it earned Hulse and Taylor the Nobel Prize in Physics in 1993. But woven into all of those timing measurements were relativistic corrections. Gravitational time dilation, the relativistic Doppler effect, the Shapiro delay where the pulsar's signal takes a little longer to reach us when it passes through the curved spacetime near its companion. Every one of those effects had to be modeled using Einstein's equations, and every one of them checked out beautifully. Think about what that means. A theory that Einstein developed in 1915, sitting in Berlin during the First World War, working through tensor calculus with the mathematical framework he'd learned from Marcel Grossman. That theory predicted, with extraordinary accuracy, the behavior of two collapsed stars whipping around each other, billions of light years worth of physics, away from anything Einstein could have imagined. That's the power of getting the fundamentals right. But neutron stars aren't even the most extreme case. You knew where this was going. Black holes. A black hole is what happens when gravity wins completely, when nothing, not even neutron degeneracy pressure, can hold the collapsing matter up. The mass compresses past a critical threshold, and you get a region of space-time where the curvature becomes so extreme that nothing, not light, not information, nothing at all can escape once it crosses a boundary called the event horizon. And at the event horizon, gravitational time dilation goes to infinity. That's not a metaphor. According to general relativity, if you watched someone falling toward a black hole from a safe distance, you would see their clock slow down more and more as they approached the event horizon. Their movements would appear to get more sluggish. Their light would redshift toward longer and longer wavelengths, and right at the horizon, they would appear to freeze. Their clock, from your perspective, would stop. They'd be smeared across the horizon in an infinitely redshifted image, fading from view. From their own perspective, of course, they'd cross the horizon without any particular drama. General relativity says there's nothing locally special about the event horizon if you're the one falling through it. You wouldn't feel a boundary. You'd just keep falling, but you could never send a signal back out. The future, for you, would point inward. That's what extreme space-time curvature really means. It doesn't just slow time, it reshapes the very geometry of what forward in time means. Now, for a long time, black holes were purely theoretical. Einstein himself wasn't sure they could actually exist in nature. Carl Schwarzschild worked out the first exact solution to Einstein's field equations back in 1916, just months after Einstein published them, and that solution described the space-time around a spherically symmetric, non-rotating mass. The Schwarzschild solution naturally contained this strange boundary, this radius below which things got mathematically peculiar. Schwarzschild himself was serving on the Eastern Front when he did this work. He sent the paper to Einstein from the trenches, and he died of an autoimmune disease shortly after. He never got to see the decades of debate his solution would inspire. For years, physicists argued about whether the Schwarzschild radius was a real physical boundary or just a mathematical artifact, a coordinate singularity that you could transform away by choosing different coordinates. It took until the late 1950s and 1960s for people like David Finkelstein, Roger Penrose, and John Wheeler, who actually coined the term black hole in 1967, to clarify the physics and show that yes, the event horizon is real, and yes, if enough mass collapses into a small enough region, a black hole must form. Penrose's 1965 singularity theorem, which earned him a share of the 2020 Nobel Prize, showed that once an event horizon forms, general relativity predicts a singularity inside, a point of infinite density, where the theory itself breaks down. But here's what's remarkable for our story about time. We now have observational evidence that black holes are real, and that space-time around them behaves exactly as Einstein's equations predict. In 2015, the LIGO detectors, those extraordinary laser interferometers with 4-kilometer arms, one in Louisiana and one in Washington state, detected gravitational waves from two black holes merging about 1.3 billion light-years away. The signal matched general relativistic predictions with stunning precision. The waveform, the frequency, the amplitude, all of it lined up with what numerical relativity simulations said two spiraling black holes should produce. And then in 2019, the Event Horizon Telescope collaboration released that famous image, the shadow of the supermassive black hole in the galaxy M87, a monster with about 6.5 billion times the mass of our sun. That glowing ring of superheated gas surrounding a dark shadow was exactly the shape and size that general relativity predicted. The photons forming that ring had been bent, lensed, and time-delayed by the extreme curvature of space-time around the hole. And here's a detail I love. The light you see in that image. Some of those photons have orbited the black hole one or more times before escaping toward us. They've traveled through regions where time, relative to us, was running dramatically slower. The image itself is a kind of temporal composite, stitched together from light that experienced different amounts of gravitational time dilation depending on how close it passed to the event horizon. The very picture is a portrait of warped time. So we've come a long way, haven't we? From Pound and Rebka measuring a shift of a few parts in 10 to the 15th over 22.5 meters, to GPS satellites correcting for 38 microseconds a day, to optical clocks detecting time dilation over the height of a step stool, to neutron stars where time runs 30% slower, to black holes where time dilation becomes infinite at the horizon. It's all the same physics, the same curvature of space-time, the same insight that Einstein had in that patent office in Bern, that gravity and acceleration are the same thing, and that this equivalence has profound consequences for the nature of time, and that progression, from the barely detectable to the cosmically dramatic, tells you something deep about how the universe is structured. General relativity isn't just a theory for exotic objects. It's the operating system of space-time itself. It governs the timing of your GPS fix and the death spiral of merging black holes with the same set of equations. And as our instruments get more sensitive, we keep finding that Einstein was right in regimes he never could have tested himself. But there's one more piece of this story that I want to share with you, because it brings everything full circle in a way that I think is genuinely beautiful. It has to do with something that might seem unrelated at first, the detection of gravitational waves themselves, and what they tell us about the nature of time. Because gravitational waves aren't just ripples in space, they're ripples in space-time. They stretch and compress time itself as they pass through. And when LIGO detected that first signal in September 2015, the tiny oscillations in the lengths of those 4-kilometer laser arms, oscillations smaller than 1,000th of the diameter of a proton, those oscillations were, in a very real sense, fluctuations in the rate at which time was passing at different points along the detector. The mirrors at the ends of the arms weren't just moving through space. The space-time between them was being stretched and compressed rhythmically, like the fabric of reality itself was breathing. And that's not a metaphor. That's literally what was happening. The gravitational wave was a traveling distortion in the geometry of space-time, and as it washed over the detector in Livingston, Louisiana, and then 7 milliseconds later over the one in Hanford, Washington, it was briefly changing how much time elapsed between the mirrors. Tiny, impossibly tiny amounts of time, but real, measurable, confirmed. And here's what I find so satisfying about that. Think about the journey we've taken. We started with Einstein sitting in a patent office, imagining a person falling off a roof. That thought experiment led him to the equivalence principle, which led him to predict that clocks in a gravitational field run at different rates. Then Pound and Rebka confirmed it across 22.5 meters of a tower at Harvard. Then Huffell and Keating confirmed it by flying atomic clocks around the world. Then GPS turned it into infrastructure, something your phone depends on every single day without you ever thinking about it. Then, optical lattice clocks pushed the sensitivity so far that you could detect the difference in the flow of time across the height of a single step on a staircase. And then, at the extreme end, we looked at neutron stars and black holes, where the curvature of space-time becomes so intense that time dilation isn't a subtle correction anymore. It's a dominant feature of the physics. And now, with gravitational waves, we've come to something even more remarkable. We're detecting the dynamic oscillation of time itself, propagating across the universe at the speed of light, carrying information about the most violent events in the cosmos. So, let me slow down and talk about what gravitational waves actually are in terms of time, because I think this is one of those things that gets glossed over a lot. When people hear about LIGO, they usually hear about the stretching and squeezing of space. And that's accurate. But it's only half the story. A gravitational wave is a perturbation in the metric of space-time. The metric is the mathematical object that tells you the distance between two events. And by events, I mean points that have both a location in space and a moment in time. So when a gravitational wave passes through, it doesn't just change spatial distances. It changes the full four-dimensional relationship between events. It modulates time intervals too. The reason LIGO is usually described in terms of spatial stretching is that the detector is designed to be sensitive to changes in the spatial length of its arms. That's what the laser interferometer measures. But the underlying physics is a distortion of space-time, not just space. And this is where it gets kind of mind-bending. Think about two clocks sitting side by side, perfectly synchronized. A gravitational wave passes through. Depending on the orientation of the wave relative to the clocks, the rate at which those clocks tick can briefly diverge by an almost inconceivably small amount and then converge again as the wave passes. The wave is literally modulating the flow of time as it moves through. It's a traveling ripple in the temporal fabric of the universe. And the fact that we can detect this, that we've built instruments sensitive enough to register these whispers of space-time geometry, that's one of the great engineering achievements of the 21st century. Let's talk about that engineering for a moment, because LIGO is, in many ways, a monument to precision. Each of the two LIGO detectors has two arms, each 4 kilometers long. A laser beam is split and sent down both arms, bounces off mirrors at the far ends, and recombines. If the arms are exactly the same length, the light waves cancel out perfectly when they recombine. Destructive interference. But if a gravitational wave passes through and stretches one arm while compressing the other, even by an almost unimaginably small amount, the light waves arrive slightly out of phase, and you get a signal. The sensitivity required is staggering. LIGO needs to detect changes in arm length on the order of 10 to the minus 19 meters. That's a 10,000th of the diameter of a proton. To put that in perspective, if you scaled LIGO's arm up to the distance from Earth to the nearest star, about 4 light-years, the displacement you'd need to detect would be about the width of a human hair. The engineering challenges involved in achieving that are almost absurd. You have to isolate the mirrors from every conceivable source of vibration: seismic noise, traffic on nearby roads, ocean waves hitting the coast hundreds of miles away, even the quantum fluctuations of the laser light itself. The mirrors hang from quadruple pendulum suspensions made of fused silica, each stage filtering out vibrations. The laser is stabilized to a degree that would have seemed like science fiction 20 years before the detector was built. The vacuum system enclosing the laser path is one of the largest high-vacuum systems ever constructed. The tubes are about 1.2 meters in diameter, and they maintain a pressure about a trillionth of atmospheric. All of this, every bit of it, is in service of detecting a fluctuation in the geometry of space-time, and the person who more than anyone else made LIGO happen was Rainer Weiss, a physicist at MIT. Weiss first sketched out the basic concept of a laser interferometer gravitational wave detector in 1972 in a document that's sometimes called the Weiss paper, but was actually an internal MIT report, Quarterly Progress Report number 1/05. It laid out the noise sources, the required sensitivities, and the basic design. It was remarkably prescient. But getting from that concept to a working detector took over 4 decades and roughly $1 billion of funding, most of it from the National Science Foundation. Along the way, there were bitter disputes about management, about design choices, about whether the whole thing would even work. Kip Thorne at Caltech had been pushing for gravitational wave detection from the theoretical side since the 1970s. Ronald Drever, a brilliant and difficult Scottish experimentalist, joined Caltech and contributed crucial ideas about the optical configuration. The three of them, Weiss, Thorne, and Drever, are often credited as the founders of LIGO, and Weiss and Thorne shared the 2017 Nobel Prize in Physics for the detection. Drever, sadly, had developed dementia by then and couldn't fully appreciate the recognition. He passed away in 2017, just months after the Nobel announcement. It's one of those bittersweet stories that runs through the history of physics. The person who helped make the breakthrough possible not quite being there to see it acknowledged. But the real hero of the LIGO story, in many ways, is patience and stubbornness. Because for decades, a lot of the physics community thought LIGO was a waste of money. The signals were predicted to be so small that many serious physicists doubted they could ever be detected. There were review panels and funding battles and moments when the whole project nearly got canceled. The initial version of LIGO, which operated from 2002 to 2010, detected nothing, not a single gravitational wave. And that was actually expected. The initial design was meant to prove the technology could work, not necessarily to make a detection. But you can imagine how hard it was to go to Congress and say, "We spent hundreds of millions of dollars. We ran the detector for 8 years, and we found nothing. But trust us, the upgraded version will work." And yet, that's exactly what happened. Advanced LIGO, with dramatically improved sensitivity, came online in September 2015, and within days, literally within days of being turned on for its first observing run, it detected the signal from 2 black holes merging 1.3 billion light-years away. The signal lasted about 0.2 of a second. The black holes were about 36 and 29 solar masses, and they merged to form a single black hole of about 62 solar masses. If you do the math, you'll notice that 3 solar masses are missing. That mass was radiated away as gravitational wave energy, 3 times the mass of our sun, converted entirely into ripples in space-time, in a fraction of a second. The peak power output of that merger, for a brief instant, was about 50 times the combined luminosity of every star in the observable universe. Let that sink in. 50 times the light output of every star you could ever see, in every galaxy, in every direction, but radiated as gravitational waves, not light. And we detected it as a change in the length of a 4-kilometer laser arm by less than 1,000th of the width of a proton. Now, you might be wondering what all of this has to do with time dilation specifically. And here's the connection. Those gravitational waves carry encoded in them the entire history of the space-time curvature around the merging black holes. The waveform, the shape of the signal as a function of time, tells you about the masses of the black holes, their spins, their orbital dynamics, and crucially, the extreme time dilation happening in the region around them. When two black holes spiral toward each other, the gravitational time dilation near their event horizons is enormous. The gravitational waves emitted from that region are, in a sense, redshifted by the very curvature that produces them, and the way the frequency of the wave chirps upward as the black holes get closer, that characteristic rising tone that LIGO detected, is a direct signature of the changing space-time geometry, including the time dilation effects. When physicists extract physical parameters from a gravitational wave signal, they're using general relativity's predictions about how time and space behave in the strong field regime. Every parameter they extract is a test of Einstein's equations in conditions of extreme curvature, extreme velocities, and extreme time dilation. And so far, every signal LIGO and its European counterpart Virgo have detected has been consistent with general relativity's predictions. No deviations, no surprises. Einstein keeps being right, and this matters beyond just confirming a theory, because there are good reasons to think that general relativity can't be the final word. It's a classical theory. It doesn't incorporate quantum mechanics, and we know that at some level, gravity must be quantum. The question is where the cracks will show up. Will it be in the behavior of gravitational waves from merging black holes? Will it be in some tiny deviation in the time dilation measured by next-generation optical clocks? Will it be in the physics of the very early universe, where densities were so high that quantum gravitational effects should have been important? Nobody knows yet, but every precision measurement of gravitational time dilation, whether it's done with a clock on a tabletop or with a gravitational wave detector spanning 4 kilometers, is a chance to find those cracks, a chance to discover where Einstein's beautiful theory finally breaks down and something deeper takes over. And that brings us to something that's been quietly developing over the last few years that I think deserves its own moment in this story. Because the tools we've been talking about, these extraordinary clocks, these gravitational wave detectors, they're starting to converge in ways that nobody quite anticipated. There's a concept that's been gaining traction in the physics community, something people are calling multi-messenger astronomy. And it's one of those ideas that sounds technical at first, but once you understand what it really means, it's breathtaking in its simplicity. The idea is this: instead of studying the universe with just one kind of signal, just light or just gravitational waves or just neutrinos, you combine them. You watch the same event with every tool you have, all at once, and you build a picture that no single instrument could ever give you on its own. And the moment this went from theoretical dream to actual reality was August 17th, 2017. That's a date worth remembering, because on that day, LIGO and Virgo picked up a gravitational wave signal, but it wasn't from 2 black holes merging. It was from 2 neutron stars spiraling into each other. The signal was designated GW170817, and it was beautiful. A long rising chirp that lasted about 100 seconds in the detector's sensitive band, much longer than the black hole mergers they'd seen before. And here's what made it historic. About 1.7 seconds after the gravitational wave signal peaked, NASA's Fermi Gamma Ray Space Telescope detected a short gamma-ray burst coming from the same part of the sky. 1.7 seconds. Think about what that means. These 2 signals, one a ripple in the fabric of space-time itself, the other a burst of electromagnetic radiation, had traveled across roughly 130 million light-years of space, and they arrived within less than 2 seconds of each other. Now, that tiny delay tells you something profound about gravitational time dilation and the nature of space-time. It tells you that gravitational waves travel at the speed of light, or so close to it that the difference is less than a few parts in 10 to the 15th. That's a direct test of general relativity's prediction. Einstein said gravitational waves should propagate at exactly the speed of light, and this one observation confirmed it with extraordinary precision. In one fell swoop, it ruled out a whole family of alternative theories of gravity that had predicted gravitational waves might travel at slightly different speeds. Years of theoretical work, entire research programs, essentially swept off the table by one measurement. And within hours of that detection, telescopes all over the world swung toward the source. They found it in a galaxy called NGC 4993, an elliptical galaxy in the constellation Hydra. Optical telescopes saw a new point of light, a kilonova, they called it, that brightened and then faded over the following days and weeks. Infrared telescopes, X-ray telescopes, radio telescopes, they all watched. And the data from that kilonova told us something we'd wondered about for decades: where the heavy elements come from. Gold, platinum, uranium, elements heavier than iron that can't be forged in ordinary stellar fusion. It turns out that when two neutron stars collide, the unimaginable pressures and temperatures create these heavy elements through a process called rapid neutron capture, or the R process, and then fling them out into space. The kilonova from GW 170817 produced something like 10 Earth masses worth of gold, just scattered it into the cosmos. The gold in your jewelry, the platinum in catalytic converters, the uranium in nuclear reactors. A significant fraction of it was probably forged in ancient neutron star mergers billions of years ago, then incorporated into the cloud of gas and dust that eventually became our solar system. But let's come back to time, because that's really what this whole story has been about. That 1.7 second delay between the gravitational wave and the gamma rays. It's a measurement of how time works across 130 million light-years of curved spacetime. Both signals traveled through the gravitational fields of galaxies, galaxy clusters, the large-scale structure of the universe itself, and they were affected by gravitational time dilation along the way. The fact that they arrived so close together constrains how gravity can modify the flow of time for different kinds of signals. It's a cosmological scale version of the Pound-Rebka experiment, in a way. Instead of photons climbing 22.5 meters up a tower at Harvard, you've got gravitational waves and gamma rays crossing a substantial fraction of the observable universe. And the consistency of their arrival times is telling you that Einstein's description of how gravity curves time is holding up even at those scales. And this convergence, clocks, gravitational wave detectors, telescopes across the electromagnetic spectrum, it's only going to get more powerful. Let me tell you about what's coming. Because honestly, the next couple of decades in this field are going to be extraordinary. On the clock side, there are groups working toward what they call portable optical clocks. Junyeh's group at Gila and others in Germany, Japan, and the UK have been developing clocks that can be taken out of the lab and into the field. Imagine mounting an optical lattice clock on a satellite. The European Space Agency has been studying a mission concept called ISOC, the International Space Optical Clock, which would put an optical clock on the International Space Station. And there are even more ambitious proposals, putting optical clocks on dedicated satellites in higher orbits, where the gravitational time dilation relative to the ground is larger and therefore easier to measure with exquisite precision. With clocks accurate to 10 to the minus 18 or beyond, you could map Earth's gravitational field from space with centimeter-level resolution. You could monitor how mass moves around inside the Earth, groundwater, magma, tectonic plates, by watching how the clock's tick rate changes over time. That's relativistic geodesy becoming a practical tool for understanding our own planet. And then there's the gravitational wave side. LIGO and Virgo are being upgraded continuously. The next major step is called A-sharp, or A-sharp, an upgrade to advanced LIGO that should roughly double its sensitivity. But the real leap comes with next-generation detectors. There are two major proposals on the table right now. One is the Einstein telescope, a European project that would be built underground, probably in the border region of the Netherlands, Belgium, and Germany, or possibly in Sardinia, with arms 10 kilometers long arranged in a triangular configuration. The other is Cosmic Explorer, an American concept with arms 40 kilometers long, 40 kilometers, 10 times the length of LIGO's current arms. These detectors would be sensitive enough to detect binary black hole mergers essentially anywhere in the observable universe. They'd see neutron star mergers out to enormous distances, and the precision of their waveform measurements would be so high that they could test general relativity's predictions about gravitational time dilation in the strong field regime with 10 to 100 times the precision we have now. Here's the thing about that. Right now, Einstein's theory passes every test, but physicists have calculated that quantum gravitational effects, whatever quantum gravity turns out to be, might show up as tiny corrections to general relativity's predictions. These corrections would be incredibly small, perhaps proportional to the Planck length divided by the size of the black hole, or some similar ratio involving fundamental constants. With current detectors, those corrections are way below the noise floor. But with Cosmic Explorer or the Einstein telescope, some of those corrections might just barely peak above the threshold of detectability. Maybe. Nobody's sure. And that's what makes it so exciting. We're building instruments that are reaching into the regime where new physics might live. And there's another approach that I find really beautiful, and it connects all the way back to where we started this whole conversation. Remember how we talked about the equivalence principle? Einstein sitting in the patent office in Bern, imagining a person falling off a roof, realizing that during the fall they wouldn't feel their own weight. That simple thought experiment that started everything? Well, there are experiments being planned right now to test the equivalence principle with quantum systems, with atoms in superposition, with entangled particles, with systems that are fundamentally quantum mechanical. Because here's the deep question. Does a quantum particle in a superposition of two different heights experience gravitational time dilation in the way general relativity predicts? Does the clock of an atom tick differently when the atom is in a quantum superposition of being in two places at once in a gravitational field? This isn't science fiction. A group led by Holger Muller at Berkeley has done experiments with atom interferometers, devices that split the quantum wave function of an atom so it travels along two different paths at two different heights simultaneously, then recombines the paths and looks at the interference pattern. The phase shift in that interference pattern depends on the gravitational time dilation between the two paths. And they've measured it. They've confirmed that atoms in quantum superposition experience gravitational time dilation consistent with general relativity. but the precision is still limited, and pushing it further could reveal where quantum mechanics and general relativity start to disagree. There are proposals to do these experiments in space, where you can have longer free-fall times and larger separations between the two paths. The European Space Agency has been funding studies on space-based atom interferometry. NASA has its own programs, and if these experiments ever reach sufficient precision, they might give us the first experimental hint of how to unify quantum mechanics and gravity, the great unsolved problem of fundamental physics. So think about where we've traveled tonight. We started with Newton, with his idea of absolute time flowing uniformly everywhere, a cosmic clock that ticks the same for everyone, regardless of where they are or what's happening around them. And that idea worked beautifully for 200 years. It got us through the Industrial Revolution. It let us build bridges and steam engines and predict the motions of planets. But then Einstein came along and said, no, time isn't like that at all. Time is flexible. Time is personal. Time depends on where you are in a gravitational field, on how fast you're moving, on the curvature of the space-time you're embedded in. A clock on a mountaintop ticks faster than a clock in a valley. A clock near a black hole nearly stops. And this isn't some exotic theoretical curiosity. It's the reason your phone knows where you are. It's woven into the satellites orbiting above you right now. It's confirmed by clocks so precise they can detect the difference in the flow of time between your head and your feet. We talked about Pound and Rebka in their tower at Harvard, measuring the blue shift of gamma rays falling 22.5 meters. We talked about Haffel and Keating carrying atomic clocks on commercial airliners. We talked about the GPS engineers who had to build relativistic corrections into every satellite or the whole system would drift by kilometers per day. We talked about Jun Ye and his strontium lattice clocks, so sensitive they can feel the curvature of space-time across a tabletop. We talked about neutron stars, where time runs measurably slower, and black holes, where it stops altogether at the event horizon. We talked about LIGO, about Rai Weiss and Kip Thorne and the decades of work it took to hear the universe vibrate, and about how every gravitational wave detection is a test of how time behaves in the most extreme conditions nature can produce. And all of it, every experiment, every detection, every confirmation, traces back to that one insight Einstein had in 1907. A person falling freely doesn't feel gravity. Therefore, gravity and acceleration are the same thing. Therefore, gravity must affect time. It's one of the most beautiful chains of reasoning in all of human thought, and more than a century later, we're still following it, still testing it, still discovering new consequences of it. The thing that gets me, the thing I keep coming back to, is how deeply strange it is that time isn't what we think it is. You're lying there right now, and time is passing for you at a rate that depends on exactly where you are in Earth's gravitational field. If you're on the ground floor of a building, time is passing for you just slightly, almost immeasurably, slower than it is for someone on the top floor. And if you could somehow watch a clock near a neutron star, you'd see it crawling. Near a black hole, frozen. The universe doesn't have a single clock. It has as many clocks as there are points in space-time, and they all tick at their own rate, determined by the curvature of the space-time around them. And yet, from that strangeness, from that flexibility of time, comes everything. The orbits of planets, the bending of starlight, the ripples of gravitational waves, the structure of the universe itself. It all follows from the geometry of space-time, from the way mass and energy tell space-time how to curve, and curved space-time tells matter how to move. And time, our most intimate experience, the thing we feel passing with every breath, every heartbeat. Time is part of that geometry, not separate from it, not floating above it, woven into it. So as you drift off tonight, maybe carry that thought with you. The time you're experiencing right now, this very moment of drowsiness, of your thoughts getting softer and slower, that's not happening in some abstract universal time. That's the same everywhere. It's your time. It belongs to your particular path through the curved space-time of this planet, this room, this exact spot where you're resting. And it's flowing at a rate that Einstein's equations can predict to extraordinary precision. Every second you experience is a little act of gravity, a little expression of the curvature of the universe around you. And that's not just beautiful physics. That's your life, happening in curved space-time, one gentle tick at a time. So let that thought settle. Let it be soft, and let the quiet take over from here.